So the next speaker is Professor Tosatti. The title of his third lecture is Introduction to the Kähler-Ricci flow.
Okay, thank you again, and welcome to the last lecture. So maybe this is the first slide, but maybe I should go back 1 second, since it was maybe 2 days ago. So what we were talking about, let me see if I can, yes, okay, go back. So we discussed in the previous lecture, sorry, I will stop soon, here, the maximal existence time of the Kähler-Ricci flow, which was this result by Tsuji and Tian and Zhang, that on a compact Kähler manifold, X, you start the Kähler-Ricci flow at an initial metric omega 0, which is scalar, and then the flow exists for time exactly capital T, where capital T is computed in cohomology. You look inside the Kähler cone here, and you look where the class of the flow, which is the initial class minus 2 pi T C1 of X, as long as this class remains inside the Cx, which is the cone of cohomology classes that admit a Kähler metric, right? So this is computed in cohomology, and it's infinite if and only if minus the first Chern class, which is the direction of this segment, belongs to the closure of the Kähler cone. And the last time we discussed the case of finite time singularities. I'm going forward. In particular, I give you the idea with some details of the proof of this conjecture, Feldman, Inman, and Knopf, about the singularity formation set when you have a finite time singularity. So the singularity formation set, roughly speaking, is where the curvature blows up at the singular time. And we proved that it is a closed analytic subvariety. And actually, it's equal to the union of all the irreducible analytic subvarieties V, whose volume is shrinking to 0 at the singularity. So, okay, so now with this reminder, we can say a few more things about the case of finite time singularities. So first of all, I want to discuss the case of finite time collapsing. Namely, the singular set sigma, we just proved, is the union of all the subvarieties whose volume shrinks to 0. But that may be, and we proved that it's a closed analytic subvariety of X, but I didn't say proper. So it could be all of X. And indeed, sigma is equal to the whole manifold, if and only if the volume of the whole manifold shrinks to 0 at time t. And this certainly happens. I think we saw already the case of the Riemann sphere, CP1, which in finite time shrinks to a point. The total volume goes to 0. So the theorem in that case says that the curvature blows up everywhere because the singularity formation set is everything. And in any case, when this happens, we say that we have a finite time collapsing. Whenever you have the solution exists only over finite time and the volume goes to 0 at that time. Now, when should these finite time singularities arise? So we made a precise conjecture, which was kind of folklore, but wasn't made very precise in the literature before with the Yuguang Zhang a few years ago. So a compact Kähler manifold X has some solution of the Kähler-Ricci flow, which has finite time collapsing, if and only if X admits a Fano fibration, which I will explain now. So as in this picture, that's a fibration over a base, which may have singular fibers. It's a holomorphic map, surjective. And the generic fibers of this map are a Fano, which means that the first Chern class is in their Kähler cone. Or equivalently, by the Yau's theorem, the generic fiber admits a Kähler metric with positive Ricci curvature. So here I picture them as kind of spheres, the generic fibers. So if your manifold is fibered by Fano manifolds, submanifolds, perhaps with some singular fibers, then it is not hard to see that one can find a solution of the Kähler-Ricci flow which exhibits finite time collapsing by shrinking these fibers. And the conjecture is really the converse. So if you have a solution of the Kähler-Ricci flow with finite time collapsing, then one should prove that there is such a fibration structure. And using methods of the minimal model program for Kähler manifolds, we prove this conjecture in dimensions up to 3 with Yuguang. So certainly it should be expected to be true in general. Notably, one can phrase this conjecture so that it doesn't really involve the Kähler-Ricci flow. So it's conceivable that one should prove this without using the Kähler-Ricci flow in any way. So the assumption of the Kähler-Ricci flow of finite time collapsing can be restated without the flow. And indeed, our proof here doesn't use the flow. So it's actually more of a conjecture in complex analytic geometry. So in any case, the point is, if you have this Fano structure, then you will have some solutions of the Kähler-Ricci flow that exhibit finite time collapsing. And then one can still ask for the behavior of these solutions. And this is actually very mysterious. So in general, there are very few results about this. One expects that if one runs the Kähler-Ricci flow on this X, which has the Fano vibration, and you need to assume that your initial metric is chosen so that in finite time, the cohomology class becomes the pullback from the base of a Kähler class. So that corresponds to the fibers that should shrink in finite time, at least in the sense of cohomology. Then one expects that indeed the fibers will shrink in the sense of metric. So the metric restricted to the fibers is going to 0. And you should converge suitably to a limiting metric that is pulled back from the base. So the fibers should completely disappear in finite time. And this part was only proved in very special cases, which are projective bundles. So when there are no singular fibers and the Fano fibers are projective spaces by Song, Sekihide, Weinkov, with a later improvement by Fu and Zhang and C.C. Shen, who also can deal with some other Fano fibers. But in general, we still don't have the optimal results even here, even in the case of CP1 cross CP1 or S2 cross S2. If you start the Kähler-Ricci flow on S2 cross S2 with a Kähler metric that gives different volumes to the two S2 factors, then the precise behavior of the flow is not known in general. And also, if one restricts to the fiber, one of these smooth Fano fibers, the flow shrinks it, but you can rescale it. So you can look at the flow, restrict to the fiber and rescale by the time to blow up. So now this has a fixed size, and one expects this should converge, at least in some sense, to a Kähler-Ricci soliton, which is a homothetically shrinking solution of the Kähler-Ricci flow. And this was proved by Perelman in the only case is when the base Y is a point. So there is the most degenerate case is when X is a Fano manifold, which maps to a point. There is a Fano vibration, you can say, of a trivial type. And in that case, that's exactly what Perelman proved, actually in unpublished work, but it was later written up by Natasha, Sheshum, and Tian. So it's known basically when there's only one fiber. Okay, so this is a really challenging case to study. One of the challenges is that the limiting metric on Y is not expected to be canonical in any sense. It will depend very much on the initial metric on X that you pick. So it doesn't satisfy any canonical PDE on the base. And this certainly doesn't help. So on the other hand, for finite time non-collapsing, things are quite a bit better. So this is the other case when you have a finite time singularity and the volume doesn't shrink to 0, it stays positive, which, as we know now, is equivalent to saying that the singularity formation set is not all of X. So it's a proper closed analytic subvariety. So it's small. And in this case, we conjecture with Simeon Philip, again, this doesn't really, it can be translated into a conjecture that's not about the flow, that this, if you have such a finite time singularity non-collapsing, then you can contract the singularity formation set in the sense that you can find a holomorphic map from X to Y, where Y is a Kähler manifold or possibly singular Kähler space, analytic space, like in the lectures of Vincent, which is an isomorphism on the complement of sigma, and it's not an isomorphism at any point of sigma. So sigma is contracted, meaning that each irreducible component of sigma will be mapped to something of lower dimension, but they don't have to be necessarily points. So here is a schematic picture where sigma will be these spheres. When you approach the singular time, the volume is getting smaller and smaller, and then at the singular time, they disappear. and this would be the new space Y. So this conjecture is known. So we proved it with Simeon when n is equal to 2. Even there, it's not obvious, actually. Soon afterwards, it was proved by Andreas Oehring when n is equal to 3, again, using techniques from the minimal model program for Kähler manifolds. So again, it's certainly expected to be true in general. And it's also known, I didn't put it on the slide, if X is algebraic, projective, and if the limiting class of the flow is a rational class, then this is also known by more standard algebraic geometry, Kawamata and Shakurov's space point free theorem and other things there. So, so it is known in many cases. And then what should the flow do? So as we said earlier, on the complement of sigma, which now is almost the whole manifold, we know that we have smooth convergence. We proved it in the previous class to some Kähler metric omega t that only lives on x minus sigma. And then one expects that in the sense of metric spaces, this is called Gromov-Hausdorff, the Kähler-Ricci flow should converge to the metric completion of this limiting metric. So x minus this singularity set, and take the metric completion of the limiting metric. And that this metric completion, which is part of the conjecture, is a compact metric space, should be homeomorphic to Y, where Y is this contracted space here. And this is proved in the case where this contraction is assumed to exist and it's assumed to be a blow-up of a point or of a smooth submanifold. So the blow-up of a point was Song and Weinkoff. The blow-up of a submanifold was Bingguo more recently. And in general, these contractions, even when they exist, may be extremely complicated. So there is the still partial progress by Song and Tian, who essentially conjecture this whole picture. And they conjecture that this process can be repeated finally many times by restarting the Kähler-Ricci flow, maybe not quite on Y, which maybe have too strong singularities, but on some new Kähler space Y prime bimeromorphic to Y. So this corresponds to some kind of complex analytic surgery where you pass from X to Y prime. And they conjecture also that these surgeries should be, at least in the projective case, should be the same as the ones of the minimal model program by rational geometry. Oh, sorry, Gilberto was asking, I missed it, sorry. Is sigma the null locus of the second lecture? Yes, exactly. So sigma here is the singularity formation set. So let me switch back to the previous slide. Is exactly the null locus of alpha, where alpha is the limiting cohomology class of the Kähler-Ricci flow, this one here. Yeah. Okay, I go back. So that's what these spheres picture here are the null locus, which is exactly those whose volume was shrinking to 0. Okay, the Song and Tian conjecture that at least when X is projective, you can perform these surgeries and they will be exactly the ones of the minimal model program. And the process can then be repeated finally many times until either you end up in the finite time volume collapsing situation, so where you expect to have this fan of vibration, or you end up with a time equals infinity after finally many steps. So one of the technicalities, of course, is that even when X is smooth, after the first surgery, if you can construct it, Y prime is not smooth anymore. So it's actually better to set up everything in the category of spaces with the type of singularities that will arise. And that's, I think, what Van Sant discussed in his lectures. All right, so in some sense, there are conjectures that you can follow the minimal model program using the Kähler-Ricci flow, and it should perform the same surgeries that the minimal model program does, which are called the flips and the divisorial contractions. Yeah, so this is, again, not known in general. All right, so here, let's look at one example of this, which is the same example from the previous lecture, where we blow up CP2 at a point. So E is the exceptional divisor. And we can also express X as a P1 bundle over P1. It's the projectivization of the hyperplane bundle over P1. So it also has the structure of a Fano fibration over P1. X itself is also Fano, so it also has another structure of a Fano vibration over a point. So it has two Fano vibration structures. And the Kähler cone was discussed in the previous lecture, and these yellow lines are the Kähler-Ricci flow, because that's the first class here. So there are three regimes that we discussed. They all always have singularity in finite time. If you start with a red class, where the x coordinate is bigger than 3y, we know that you have finite time volume non-collapsing, and the flow has then the null locus sigma is exactly this E. The flow converges smoothly away from E, and then the Gromov-Hausdorff limit is the symmetric on CP2. So you have performed this picture here, where you have one of these exception devices, a sphere that contracts in finite time. If you start in the blue region, where you hit this wall in finite time, you have finite time volume collapsing. And here you're exactly in the situation from 2 slides ago, where you have the Fano vibration F to P1, and the flow shrinks the P1 fibers in finite time and converges Gromov-Hausdorff to a metric on P1. So you have exactly implemented this situation here. So the first one was proved by Son-Weinkopf, the second one by Son-Sekihide-Weinkopf. And finally, the third case, when you are exactly here and you hit the vertex or the apex of this cone, when x is equal to 3y, this is where you have finite time volume collapsing, and you are shrinking the whole manifold to a point. So you are implementing this Fano vibration picture to the Fano vibration of x to a point. So x itself is Fano, and you're shrinking it to a point. And this is the case proved by Perelman, the green case. So on this blow up, you see 3 different behaviors according to where you start the flow, in which initial Kähler metric. Okay, so at least in this case, we understand things quite well. Although I should say that in the blue case, you still don't have a complete information exactly of what you would like to know. So it's still not totally solved in the blue case. So here are some, before we go to infinite time, here are finally some more conjectures about finite time singularities that would be really nice to solve. So in this slide, x will just be compare Kähler, omega 0, the initial metric of the flow, and we assume that you have a finite time singularity, which may be volume collapsing or non-collapsing. So the first conjecture is, if you write the flow as a few slides ago, maybe I can show it 1 second. As a scalar equation like this, right? So you fix reference forms, omega hat t, they're not really metrics, but they're in the correct homology class. Then you obtain this scalar Monge-Ampere equation with this potential phi t. Okay, I go back. Then the potential phi t should
Valentino, excuse me.
Yes.
There is a
yes,
question.
Yes.
There's a question.
Okay. Yes. All right. Yes. Are the fibers of conjectures have some key stability property? Yeah, not really. Yes, that's a good question. So the Fano vibration really can have any Fano fibers you want. So sometimes they will be k-stable. So let's say they will have Kähler-Einstein metrics. In that case, the Kähler-Ricci flow restricted to the fibers and rescaled is conjecture to converge to the one of the Kähler-Einstein metrics on these fibers. But in other cases, you can also have vibration where the Fano fibers are not k-stable. They don't have Kähler-Einstein. And the point is that the flow will converge to some Kähler-Ricci soliton on the fiber after rescaling with some singularities and possibly with a jump of the complex structure. So it's known now that if you have one fixed Fano manifold, this was known as the Hamiltonian conjecture, and you run the Kähler-Ricci flow normalized in the anti-canonical class, then you always converge, even when it's unstable, you always converge in some sense to a Kähler-Ricci soliton, which may have singularities and may be on a different complex manifold, in fact, even complex variety, because the complex structure will jump. So that's exactly what's expected to happen, that the fibers may not have Kähler-Einstein metrics or even smooth Kähler-Ricci solitons, and the flow rescaled will perform this jump. Yeah. So Fano vibrations, you can find them, just by taking the stupidest one would be products. So you can take your favorite Fano unstable and take the product with anything else, and that the projection to the second factor will always be a Fano fibration with my definition. Okay, so, but yeah, it's a good question. So I was saying that the potential is conjectured to be uniformly bounded below all the way up to the singularity. And I didn't write it here, but we basically proved in the previous lecture that the potential is always bounded above. That's always true. So the conjecture really says that the potential should be uniformly bounded. And this is actually tightly related to the conjecture in the previous slide. So it's again known for n is equal to 2 with the work with Philip, and n is equal to 3 by Andreas Oehring. It's also known if the limiting class has a smooth semi-positive form, closed, of course, that represents the class. And hopefully this is always true. So if you believe, how to go back? For example, if you believe this conjecture, then it's always true in the case of finite time non-collapsing. And if you believe the other conjecture, it will be true also in the case of finite time collapsing. So in some sense, if you prove both of these conjectures, then this one follows, but maybe there's potentially some way to prove this without going through those conjectures. In any case, the potential is expected not to blow up. A more geometric conjecture, which is folklore, is that the diameter of the evolving matrix should not blow up as you reach a finite time singularity. So this is been basically motivated by this Song and Tian program, that in finite time, either you have this Fano fibration where you should collapse to the base and the diameter shouldn't blow up, or you have these finite time surgeries where again you don't expect the diameter to blow up. But other than that, there's no general method established to prove this. And this is also known in very limited cases, basically when X is a finite time non-collapsing, which is the blow up of another Y at a point or at a submanifold. And you assume that the limiting class comes from Y. So in general, I don't see any obvious method to attack this in general, but it's certainly conjectured to be true. It would be very nice to know. And a related conjecture by Tian, I didn't write it, sorry, is that the diameter goes to 0 in finite time. So this can be called finite time extinction. So you can ask, when does this happen? The manifold, the flow exists for finite time and the diameter goes to 0, which means in Gromov-Hausdorff, you just see a point, your whole manifold disappears. Well, that should happen if and only if X is Fano and your initial class is a positive multiple of the first-term class. And one can actually see that the positive multiple must be 2 pi times the maximum existence time. Actually, this is equivalent to saying that the limiting class alpha, that I keep calling alpha, is the 0 class. So this situation is, sorry if I go back, is exactly the situation where you end up in the apex or vertex of this cone, Kähler cone, in finite time. So this conjecture, probably the easiest one, I would guess, to prove. This is known in general when was first proved by Jan Song, when X is projective and the initial class is rational. Then he proved this using this Kawamata's base point free theorem, which is where these two assumptions are used. And we proved it with the Yuguan Zhang in low dimensions in general, for dimensions up to 3. So it is quite possible that one can find some trick to prove this in general. You can look at our paper. It turns out that one direction here is trivial, or okay, sorry, proved by Perelman, so not trivial at all. And the difficult direction is that if you have finite time collapse extinction, then you are Fano and proportional. And it suffices to show that if you have finite time extinction, then H20 or H02 is the same. The Dolbeault cohomology H20 vanishes of X. So it's reduced to a cohomology vanishing statement. So perhaps it's more approachable. Okay, so with this, we can move to the last big topic, which is infinite time solutions. And this is actually where most of the very recent progress has happened on the Kähler-Ricci flow. So most of the recent results that have been proved in the past few years, especially since I wrote the lecture notes, there has been a lot of progress in this area. So we assume, as I said, that T is infinity. So as we know from earlier, this happens if and only if minus the first-chain class is in the closure of the Kähler cone. This condition is easy to check. If you like algebraic geometry, this is saying that the canonical bundle is F, at least when X is projective, but one can make sense of this also in the Kähler case. There are many, many examples of these manifolds, for example, tori, Riemann surfaces of genus 1 or more, smooth hypersurfaces in Pn+1 with degrees sufficiently large, bigger than n+2, and more. And as we discussed also last time, once you exist for all time, you can look at the growth of the volume. And we proved last time that it grows polynomially, like t to the m, where m is some exponent which is between 0 and n, the dimension. And it's exactly given by the largest power, such that minus the first-chain class to the k is non-zero in cohomology. I mean, you can drop this minus, but it's best to keep it so that you know that this class is F. So there are n+1 cases, you can say, to consider. But as last time, we will bundle a lot of them. So we will just consider 3 cases. The m is equal to 0, m is equal to n, or the intermediate cases. Right. So the first one that was actually proved in the very first paper on the Kähler-Ricci flow by White and Cao in '85 was the case when the volume growth is m equals to 0. So the volume is comparable to 1, meaning that the volume is bounded above by some constant. So this actually one can show easily happens if and only if the first-chain class actually vanishes. So this is called Calabi-Yau. So X is a Calabi-Yau manifold. And in this case, for Calabi-Yau manifolds, White and Cao proved that, well, of course, a posteriori, once you're Calabi-Yau, since C1 is 0, the volume is not just bounded above, but it's actually constant. And in this case, he proved that if you start with any initial metric, you converge smoothly to a limiting Kähler metric, which is homologous to the initial metric, and the Ricci curvature is 0. So the Kähler-Ricci flow evolves any initial Kähler metric on Calabi-Yau and makes it become Ricci flat in the limit. And these are, of course, the ones constructed by Yau in the 70s. So this is the best possible result, and it gives you everything. In fact, you can say more. You can say that this converges. The convergence rate is exponentially fast, which wasn't said explicitly in his paper, but it's an exercise. Okay, I see something in the chat. Oh, yes. So Gilberto was asking, yes. Since the canonical is F, yes, indeed, M is the same as the numerical Kodare dimension or numerical dimension. Luckily for Neph-line bundles, there is a unique possible notion of numerical dimension in the sense that for other, say, pseudo-effective line bundles, there are many different notions and they all agree in the Neph case. So yes, yeah, it's the numerical dimension. Okay. So, oops, the next case is the other endpoint when m is equal to n. So this happens if you look back at the formula. Well, okay, maybe I don't go back. The formula for the volume growth from the second lecture, you will see that that's meaning that this coefficient must be positive. That's equivalent to the self-intersection of the canonical bundle, if you want, being strictly positive. And this condition is called the general type. I mean, together with an Fness, you get minimal general type. That's the saying that minus C1 of X is Nef, and with this positive self-intersection. So you're running the Kähler-Ricci flow on smooth manifolds, which are minimal in general type. These are automatically projective, by the way. And then in this case, one has the following theorem proved with greater degrees of generality by Huaidong, Cao, Tsuji, and Tian and Zhang. So if you look at the Kähler-Ricci flow omega t and you divide by t, because remember the volume is growing. So if you divide by t, now the volume is roughly bounded. I mean, it's bounded. Then omega t divided by t converges to omega infinity, which is Kähler-Einstein, negative with negative Ricci curvature. Ricci omega infinity is minus omega infinity. And this converges in smooth away from sigma, the singularity formation set at infinity, which is exactly the null locus of the canonical bundle, or of minus C1 of X with the notation here. So this is exactly the union of all the irreducible analytic subvarieties of X, whose intersection with the canonical bundle is going to 0. And omega infinity is only a Kähler-Ricci metric and smooth away from sigma, and the convergence is smooth on compact sets away from sigma. And furthermore, this sigma is empty if and only if the canonical bundle or minus C1 of X is a Kähler class. So the canonical bundle is ample, or minus C1 of X is a Kähler class. And in this case, omega infinity is actually smooth everywhere, and the convergence is smooth everywhere. And this Kähler-Ricci metric was constructed by Obama and Yao, and that was Cao's original paper. So Tsuji proved this in general, but he didn't quite have a good argument for the convergence. And also, that was fixed by Tian and Zhang, and they also proved that the omega infinity has boundary potentials, which was also established soon afterwards by Esidu Zeriahi. So in general, this X is projective, as I said, and by the Kawamata-Shokuro base point 3 theorem, one can find a holomorphic map, which is birational, from X to a new variety, X-can, the canonical model of X. And this exactly contracts sigma in the previous terminology. So sigma is mapped to something smaller dimension, and this map is an isomorphism away from sigma. This is the so-called canonical model. And then the Kähler-Ricci flow, in some sense, discovers the canonical model in the following sense. If you look at the, again, omega t divided by t, the global limit as metric spaces, Gromov-Hausdorff, is actually equal to the metric completion of the smooth Kähler-Einstein metric from this theorem. So this was proved by Guosong-Weinkov in 2 dimensions, Tian and Zhou Zhang, and Zhenlei Zhang in 3 dimensions, and Bing Wang in all dimensions. And also, this metric completion is homeomorphic to the canonical model, as proved by Zhang Song. So you have nice convergence away from the singular sets. And then if you look globally as metric spaces, you exactly obtain the canonical model and the metric completion of this metric. Furthermore, Zhou Zhang showed earlier that the scalar curvature remains uniformly bounded under this process. So in this case, one knows more or less everything, let's say, that one would like to know about this. So this is a remarkable result that took the work of many people to establish. And one can say that this case is now understood. So the hardest case that remains, unfortunately, is then the intermediate case, when this volume growth or numerical dimension is strictly between 0 and n. So in this case, there is the abundance conjecture in birational geometry. Here, I will state a generalized version for Kähler manifolds. Also, I will state it in a language comprehensible for these lectures, but it can be restated in another language comprehensible to algebraic geometers. Maybe I can say it in words, but let me first read this version. So if you have a compact Kähler manifold, then the canonical boundary is F, meaning minus C1 of X is in the closure of the Kähler cone, should happen. So this, remember, means that you have a infinite time solution for any Kähler-Ricci flow on X. So this happens if and only if you can find a surjective holomorphic map with connected fibers F to a normal projective variety Y, such that minus the first class is proportional to the pullback of, let's say, the Fubini's 2D metric on Y. So some Kähler metric on Y, and lambda is some positive constant. If you don't like this, this is the same as the more familiar version, which, again, for smooth Kähler manifolds, canonical bundle is F, if and only if canonical bundle is semi-ample. So this condition here really is just repackaging the condition that the canonical bundle is semi-ample. So you should have one of these, again, fibration structures. And this conjecture is known even in the Kähler case up to dimension 3 by, well, there again, work of millions of people here, especially earlier in the 90s in the projective case. So I just tried the final theorem due to Campanacher in Peternel. But there are many, many people who worked on this earlier, and this builds upon them. So, so it's certainly expected to be true in general. And the point is, if you assume that you have this map, so you don't need to assume the abundance conjecture, right? You just need to assume that X is a compact Kähler manifold that admits this fibration. And all the known examples with infinite time solutions, they all satisfy this because there is no known counterexample to this conjecture. So you assume that your Kähler manifold X admits this map, like here. And then it's easy to see that the dimension of the base is exactly this Y. So this M, this numerical dimension, is exactly the dimension of the base. And furthermore, we can take the singularities of Y and also put together with the critical values of F on the regular part and obtain a closed proper analytic subvariety D in the base. So Y minus D is smooth. And also take the preimage S. It's a proper closed analytic subvariety of X, the so-called singular fibers. And if D here is just this dot, S is this blue fiber. And if you stay away from the singular fibers, then your map, your holomorphic map, is actually a proper holomorphic subversion. So it's a very nice map. It's a C infinity of fiber bundle. And the fibers are automatically Calabi-Yaus. So this X sub Y is going to be the fiber of Y, where Y is in the regular part. And these Calabi-Yaus are, since it's a C infinity fiber bundle, they're pairwise diffeomorphic, but in general, they're not biholomorphic. So you have a variation of complex structure phenomenon. So the picture of the fibration looks the same. Let me show it again. Looks the same as what we had for finite time collapsing, but here I pictured the general fibers as spheres. That would be Fano, positive Ricci. Now the general fibers are tori. That would be Ricci flat or Calabi-Yau. Okay, so the upshot is if you have a infinite time solution, it's conjectured that you have this, you can call it Calabi-Yau fibration structure. And all known examples have this, of course. So the simplest example of Calabi-Yau fibration is when you take the product of a Riemann surface of genus 2 or higher times a torus, C mod lambda, and the map is the 1 to sigma g. So this one here has m equals to 1, which is the dimension of the base, which is the sigma. And you can take, for example, the initial metric to be a product, in this case, of the Poincaré metric on the Riemann sphere, on sigma, product with the Euclidean metric on the torus. And in this case, you can compute the solution of the flow starting from this product metric. It's just this family of product metrics, right? So the Euclidean factor doesn't change, and the Poincaré factor grows, 1 plus 2t. And then indeed, omega t divided by t, in this case, collapses, converges to twice omega p, which is not a Kähler metric on X, right? It's degenerate. It's the pullback of a Kähler metric from the base of the fibration. So you have infinite time collapsing for this matrix, omega t over t. And this is true in general. So we prove this with the Ben Weinkow and Xiaohui Yang. If you have this vibration, Calabi-Yau vibration, with this m strictly between 0 and n, then the solution of the flow divided by t, normalized, converges locally uniformly away from the singular fibers to the pullback of a Kähler metric from the base. Omega infinity lives on y minus d, and omega infinity is almost Kähler-Einstein. The Ricci curvature is minus omega infinity plus a correction term, which is called the Weil-Peterson. Weil-Peterson form, I should say. This equation was derived by Song and Tian earlier, who proved a weaker convergence in general. So the Weil-Peterson term is a semi-positive form, which encodes the variation of complex structure of the fibers. So in particular, Weil-Peterson vanishes if and only if all the smooth fibers are biholomorphic to each other. And you can think of omega infinity as some kind of canonical metric on the base y minus d. So almost a twisted Kähler-Einstein, it's called. Yes, the weak convergence, as I said, was obtained by Song and Tian. And more recently, AC2 gets Zeriahi, which allow actually X to be singular also. So this is a more complicated situation. And the scalar curvature of omega t over t is uniformly bounded everywhere by Song and Tian in 2011. So what we proved is locally C0 convergence or collapsing. And so the picture looks like this, so the fibers really shrink for the Kähler-Ricci flow normalized like this. And one can wonder whether one has better collapsing. First of all, what we proved with Yuguan Zhang is that under this collapsing, the metric along the fiber is becoming more and more Ricci flat. Namely, if you take omega t, so if you go back, this was omega t divided by t, which is shrinking the fibers. If you remultiply by t, so the volume now is growing, then the fibers now have roughly fixed size. And what we show is that if you zoom in on one of these fibers, then in the limit you see a cylinder, a product cylinder, which is the base, which becomes Euclidean space because the base has been growing. It becomes just flat Euclidean space times the fiber where you were zooming in with the product of a Euclidean metric on the base, a product with the Ricci flat metric on the fiber. So what this means is that the Kähler-Ricci flow, when you restrict to the smooth fibers, is smoothly approaching Ricci flat metric on that fiber. So it's the analog of the conjecture for fanofibrations, that when you restrict to the fanofibers, the rescale flow should converge to a Kähler-Ricci soliton. So here it's actually a theorem. When you restrict to the smooth fibers, the rescaled flow, I mean the flow without dividing by t, will converge smoothly to a Ricci flat on the fiber. And even more, you have this cylindrical structure. So one can still ask for if you do rescale, do you have better convergence? So the conjecture here is that if you again assume this vibration, can one have that the Ricci flat, the Kähler-Ricci flow omega t divided by t collapses smoothly away from the singular fibers to this limiting canonical metric. So if you, let me go back 1 second. If you remember here, we proved that the convergence is a C0 lock for the metrics. So we proved locally uniformly. So can one upgrade this to convergence with all derivatives? So this is still open as of now. It's known in many cases. So it's known when the smooth fibers are tori. So I worked on an analogous question about the collapsing of Ricci flat metrics, which is the kind of static version of the flow. And developed techniques with Mark Grosso, Yuguang Zhang, and Hayo Hein. And then it turns out that once you have those techniques, you can often adapt them, transplant them to the Kähler-Ricci flow. So with Grosso and Yuguang Zhang a while ago, we did the case of torus fibers for the static case, and it was adapted to the flow by Frederick Fong and Zhou Zhang. And with some extra assumption that was removed with a Hein. And it's also proved when the smooth fibers are all pairwise biholomorphic, so there is no variation of complex structures of the smooth fibers, or if you want, the Weil-Peterson term is 0. Again, this was first proved by me and Hayo in the static case and adapted to the Kähler-Ricci flow by Frederick Fong and Manchun Li last year. And in general, we do know now that you have C alpha convergence. So this supersedes the result with Van Wijnkov and Xiaohui. Again, this was done in the static case by Hai and myself in 2018, and very recently extended to the flow by Zhenchun Chu and Manchun Li. And there's a related conjecture, this was raised by Tian, I think, or Song and Tian, that in the same setting, the rescaled metrics, the ones that are supposed to collapse nicely away from singular fibers, should have uniformly bounded Ricci curvature on compact sets away from the singular fibers. And so I should say first that you do not have in general uniformly bounded full Riemann curvature. So the Riemann curvature actually is known to remain uniformly bounded away from the singular fibers if and only if the general fibers, the smooth fibers, are tori or finite quotients of tori. This is actually a theorem. So the Riemann blows up in general if the fibers are not tori or quotients, but the Ricci is expected to remain bounded. And the scalar curvature is also known to be bounded, as I mentioned earlier. So as I said, both conjectures will hopefully become theorems soon by adapting the static case. So the static case was done by Hayo and myself very recently. So we proved the analogs of these results in the static case. So it just remains to adapt that to the flow, which, as you can see here, could always be done earlier. So this should be also done very soon. but as of now, they're still open. So this should be done soon. And one can also ask about the Gromov-Hausdorff limit. So the global, so this result here, a conjecture or result in some cases says that you have smooth convergence away from this singular fibers. But how about globally? So very recently, Wang Jian and Zhang Song, so two people, they proved that the rescale metrics have uniformly bounded diameter under this fibration assumption. So that's an excellent result, which analogous to the conjecture I made earlier for finite time singularities. And once you have bounded diameter, you certainly expect that you have a Gromov-Hausdorff limit. There is a compact metric space. And in some cases, this can be identified. So with Yang Li, this paper will appear very soon. We proved that in the same setup, if you assume that the base is smooth and that this discriminant D is a simple normal crossings divisor, then we show that you have Gromov-Hausdorff convergence of the flow rescaled to the metric completion of the limiting metric omega infinity on the base minus the discriminant locus. And furthermore, assuming that Y is smooth, still this metric completion is known to be homeomorphic to Y, the base of the fibration, by recent work of Song Tian and Zhenlei Zhang. So this assumption that Y is smooth and these simple normal crossings, at the very least, is certainly always satisfied when M is 1. So when the base is a Riemann surface, it's automatically smooth because it's in general it's a normal projective variety, and the discriminant locus will just be a bunch of points. So those are simple normal crossings. So that finds the Gromov-Hausdorff limit in general when the base is a Riemann surface. We actually can extend this with some slightly weaker assumption on YD, but not in general yet. And it's certainly conjecture that the same result should hold without any assumptions on Y and D. So the conjecture is that in the same setup of these fibrations, Calabi-Yau fibrations, you should have the same thing. The Gromov-Hausdorff convergence should be the metric completion of this, which should be homeomorphic to Y, even if Y is singular. So that would complete the picture in this case, if one could prove this together with the conjectures here. All right, so we get to the end, which is, as I promised, to give this table again with now the expected behavior. So if you want the summary of what we discussed about the Kähler-Ricci flow. So you in this table, of course, X is a compact Kähler manifold, and you start the Kähler-Ricci flow omega t at an arbitrary initial metric omega 0. So you have this dichotomy. So the maximal existence time is t, which is cohomological. You have this dichotomy with it's either finite or infinite. We said, let's look first at the finite. Just a recap of what we said. The finite time singularity either is volume non-collapsing, so the volume doesn't go to 0, or it's volume collapsing, so it goes to 0. So in the first case, you have the sigma, the null locus of the limiting class, or the union of the subvarieties whose volume is shrinking to 0. And as we said, one expects to perform some complex analytic surgery, so some birational or bimeromorphic map, and the flow should restart on a new projective variety or a new Kähler variety of the same dimension. And this, in the projective case, should be the same surgery as in the minimal model program. So this part is certainly open in general, but as I said, there has been progress I discussed earlier. And if we have finite time volume collapsing, one expects that X has a fan of vibration structures and the flow shrinks the fibers in this finite time. You converge to a metric on the base of the fan of vibration. And furthermore, if you rescale the flow and you restrict to a general smooth fiber, then you should converge suitably to a Kähler-Ricci soliton on that fiber, but again, possibly with a jump of the complex structure and possibly with some singularities. So these two are very much open. In my view, probably the hardest case is the Fano fibration case. This is really annoying. As I said, even the case of S2 cross S2 or P1 cross P1 is open if the volume of the two factors are not the same. And on the other hand, and there's no other, so this should be the full description. And in the first case, then you can, so in the second case, you would stop when you hit the Fano fibration. In the first case, you can continue the Kähler-Ricci flow on the new variety. Of course, if you set up the whole Kähler-Ricci flow so that it can be run on singular varieties also, as in Vincent's lectures. So the first step should be repeatable finally many times until you either hit finite time collapsing or you hit the second option, which is infinite time solutions. So those are the ones for which the canonical bundle is NEF. And you look at the volume growth and you have these three qualitative cases. The volume order of one, we said is completely understood. X must be Calabi-Yau, and you have assumed convergence to Ricci flat. This check mark says that this case is complete in some sense. Of course, one can always ask more refined questions, but at least the basic understanding is complete. And the maximum volume growth case, X is actually projective, minimal of general type, and one has convergence to a negative Kähler-Einstein with some singularities. Again, check mark here. So these two are checked. And finally, this intermediate case, one expects a Calabi-Yau fibration, and the fibers then should shrink to a limiting canonical metric on the base, and the rescalings will give you Ricci flat metrics on the fibers. So, as I said, a lot has been established here. If you assume the Calabi-Yau fibration exists, there is basically zero results or very, very few things known if you do not assume the existence of the fibration. So if you just have the Kähler-Ricci flow here, by abundance, you expect the fibration to be there, but you do not assume that you have it. What can you say? And very little can be said. So it's another good challenge to say more in that case. And to end, I should just mention, I know the time is up, that there are very much related extensions or other perspectives that one can study about the Kähler-Ricci flow. First of all, thanks to the relation with minimal model program, one is naturally led to ponder about the logarithmic case and the relative case, and the logarithmic relative case, exactly in the same sense that's done in Barashian geometry. And these have been studied recently, although not much. So the logarithmic Kähler-Ricci flow means the Kähler-Ricci flow with conical singularities along a divisor, was first studied by Liang-Ming Shen and later by my student Greg Edwards. And the relative Kähler-Ricci flow, I think there's only one paper by Robert Bierman about this. The non-compar case is a huge, huge area of study, starting with the work of Wanxiong Shi and many, many people. And I'll add as a self-advertisement, the non-Kähler case. Of course, there are many different flows. I think the pluriclose flow was mentioned by Anna, but in the non-Kähler case, one can actually study the same Monge-Ampère equation that appears in the Kähler-Ricci flow. This turns out to be a very nice flow called the Chern-Ricci flow. It was first studied in a special case as the Monge-Ampère equation by Matt Gill, a student of Ben Weinkov. And then with Ben, we introduced it in general as a DGDTs minus Ricci for non-Kähler metrics. So here, actually, many things work in a similar way as the Kähler case, but there are new challenges in the non-Kähler case. Of course, there are also other things that one can study, but these are the most obvious direct extensions of this. So with this, I will end, and thank you all for attending these lectures.
Thank you, Valentino.
Thank you.
Thank you for your beautiful three lectures.
Maybe I can put back this table. Yes.
Look, are there questions, comments, or remarks?
Oh, there was something in the chat. Sorry. Yes. Oh, right, Gilberto. Yes. Is the second item related to Mori dream spaces? Yes, more precisely, I think they're called Mori fiber spaces. But yes, so yes and no. So that's a good question. So the Mori fiber space is a Fano vibration where the relative Picard number is 1. Okay, very roughly speaking, but here one will find sometimes these Fano vibrations are Mori fiber spaces, sometimes they're not. And what this corresponds to is when you, so if you know in the minimal model program, they talk about a contraction of extremal rays in the dual cone of curves. That would be the dual, roughly speaking, the dual of the Kähler cone here, or the ample cone. So contraction of extremal rays, the contractions of vibration type give rise to Mori fiber spaces. But when you start the Kähler-Ricci flow, you may hit a face of the Kähler cone, the boundary of the Kähler cone, at a point that in the dual picture of curves corresponds not to an extremal ray, but to an extremal face, which is of dimension higher than a ray. So you could hit, so in the minimal model program, they always just contract extremal rays, but the Kähler-Ricci flow, depending on the initial metric omega 0, you may hit in the dual picture an extremal face rather than a ray. And if you hit a face which is not a ray, you obtain a Fano vibration which is not a Mori fiber space. So in some sense, generically, if you wiggle the initial Kähler metric omega 0, you change it a little bit, you should be able to only see Mori fiber spaces in these Fano vibrations. So those are the ones with the relative Picard number, it's 1. But if you are insist on looking at arbitrary initial Kähler metrics omega 0, you have to look at arbitrary points in the boundary of the Kähler cone that you hit by the flow, and they correspond to arbitrary extremal faces of the cone of curves. That's actually a technical issue. So in the minimal model program, it's very convenient to work with arrays, and that causes us a headaches here with the what is it, Yu Guang and Andreas Oering. What is it? No, it's supposed to be here, right? So with this one here with the Yuguan Zhang. So here we have to construct this Fano vibration, and the fact that you may hit a face that is not a ray in the dual picture is actually causes headaches. So that has to be dealt with, and we are able to deal with it in dimension 3, actually with help from Andreas. But yeah, that's actually an annoying point. Yeah. Okay, let me go back to the end here. Oh, there's one more question, I think. Oh, yes, there was an answer, I think.
More questions? This is not the case, so we thank again Valentino Tosatti.
Thank you all. Thank you.
Thanks.
Thank you very much, Valentino.
Thank you.